Hello dear students, welcome to Wallah. So I hope you are doing well, and this is a session on heat exchanger. So this is a one short series. So whatever the topic we discuss here, that we will cover in a one shot, right? So today's topic is a heat exchanger. So heat exchanger topic we will cover in a one shot, right? Now what are the topics that we will cover in the heat exchanger, right? What are the topics that we will cover in the heat exchanger? So that first topic is a type of heat exchanger. Basically, what is a heat exchanger and the type of heat exchanger, right? So there are different types of heat exchanger, right? We will discuss about all those heat exchangers, right? Then second one is the energy balance in the heat exchanger, right? Energy balance in the heat exchanger. Then next topic is the LMTD method, right? LMTD, that means logarithmic mean temperature difference method. And after that we will discuss about the effectiveness concept, right? And at the last we will discuss about the effectiveness NTU method. Okay, so let's start our discussion. Let's start our discussion with the that very basic definition of the heat exchanger. That very basic definition of the heat exchanger. What is a heat exchanger, right? So see, as the name suggests that heat exchanger is basically a device in which that heat exchange occurs. Heat exchange between the hot fluid and the cold fluid, right? Hot fluid gets cooled down and the cold fluid is heated. So this is a very simple definition of the heat exchanger, right? Now see, the heat exchanger is a device which is used to transfer the heat energy from one fluid to the another fluid, right? From one fluid to the another fluid. One fluid is a hot, another fluid is a cold fluid, right? That hot fluid gets cooled and the cold fluid is heated. So this is a simple definition of the heat exchanger. This is a simple definition of the heat exchanger. Okay, now come to the next part, which is a classification of the heat exchanger. Classification of the heat exchanger, right? Or you can say type of heat exchanger. So see, if I am talking about the type of heat exchanger now, heat exchangers are classified on the basis of the various criterias. Right, just a first criteria, if you see that first criteria is on the basis of the nature of the heat exchange, right? The first classification is on the basis of the nature of heat exchange, right? So if you classify the heat exchanger on the basis of nature of heat exchange, right? So there are three types of heat exchanger. There are three types of heat exchanger. That first one is a direct contact type of heat exchanger. Direct contact type of heat exchanger, that means hot fluid and the cold fluid. Hot fluid and the cold fluid come into direct physical contact, right? Hot fluid and the cold fluid come into direct physical contact, right? Hot fluid gets cooled down and the cold fluid is heated, right? So this is simple. This is simple. Direct contact type of heat exchanger. Indirect contact type of heat exchanger, hot fluid and the cold fluid come into direct contact, right? If you ask me, sir, what are the examples of the direct contact type of heat exchanger, right? So that cooling tower which is used in the steam power plant, the cooling tower which is used in the refrigeration plant, right? That is an example of the direct contact type of heat exchanger, right? Even that in a steam power plant, that open feed water heater is used. Right? That open feed water heater is also example of the direct contact type of heat exchanger, because in open feed water heater, that steam and the water come into direct contact, right? So that is also example of the direct contact type of heat exchanger, right? Apart from that, that jet condenser, that is also example of the direct contact type of heat exchanger. In jet condenser also, right, that steam, jet condenser is also used in the steam power plant, right? So in jet condenser, steam and the cooling water directly come into contact, right? So these are the some examples of the direct contact type heat exchanger, right? So first example is cooling tower. Second example is open feed water heater, right? And next example is jet condenser, etc. Right? So these are the example of the direct contact type of heat exchanger, right? Now second is storage type of heat exchanger or regenerator. Storage type of heat exchanger or regenerator, right? So in storage type of heat exchanger, hot fluid and cold fluid are not in contact at a time, right? Hot fluid, see, in a direct contact type of heat exchanger, na, hot fluid and the cold fluid are in contact at a time, are in direct physical contact at a time. But in the storage type of heat exchanger, hot fluid and cold fluid are not in contact at a time, right? What happened here, that first that hot fluid passes through some, I can say some medium, that hot fluid passes through some medium, right? And that hot fluid gives its energy to that medium, right? After that, the cold fluid passes through that medium. So what cold fluid is doing? Cold fluid is taking the heat energy from that medium, right? Basically that medium store the heat energy. That medium store the heat energy from the hot fluid, right? That medium takes the heat energy from the hot fluid, store it, and if the and when the cold fluid passes through that medium, then that medium gives the heat energy to the cold fluid. So such type of heat exchanger is known as the storage type of heat exchanger or regenerator. So here see that hot fluid and the cold fluid are not in contact at a time, right? First the hot fluid gives its energy to some another medium, and after that the cold fluid takes the heat energy from that medium, right? So basically this is the storage type of heat exchanger, right? That medium store the energy, okay? That medium store the energy, right? Which energy? That takes from the hot fluid, right? So that medium takes the heat energy from the hot fluid, store it, and when the cold fluid passes through it, right, it gives. Is it fine? So that is known as the storage type of heat exchanger or regenerator, right? So what are the example of the storage type of heat exchanger? Storage type of heat exchanger. So in storage type of heat exchanger, heat exchanger used in gas turbine power plant. Heat exchanger which is used in a gas turbine power plant, right? That is known as the regenerator only. Apart from that, air preheater used in steam power plant. Air preheater used in the steam power plant, right? So air preheater, right, before the combustion chamber, in the combustion chamber, fuel and air is required for the combustion. So the air which is passes through the combustion chamber, first it is preheated. Right? So that is the air preheater. In the device where that air is preheated is known as the air preheater. So that air preheater is nothing but the heat exchanger only, and that is a storage type of heat exchanger. So what are the example? That air preheater which is used in the gas turbine, air preheater which is used in the steam power plant, and also that heat exchanger which is used in the gas turbine power plant. So these are the example of the storage type of heat exchanger. Now next is the transfer type of heat exchanger or recuperator. See, in the transfer type of heat exchanger, or in the recuperator, hot fluid and the cold fluid are in indirect contact, right? That is not in direct contact. Hot fluid and the cold fluid are in indirect contact at a time, right? That means hot fluid and the cold fluid are separated by some means. Cold fluid and the hot fluid are separated by some means, because see, in the direct contact type of heat exchanger, hot fluid and cold fluid are in direct contact, whereas in the transfer type of heat exchanger, hot fluid and cold fluid are not in direct contact, right? Both the fluids are in contact at a time, but not in direct contact, separated by some means, right? Now see, there are certain example of the transfer type of heat exchanger. That first example is concentric tube type of heat exchanger. That first example is concentric concentric tube type of heat exchanger. Concentric tube type heat exchanger. Concentric tube type of heat exchanger. See here. If you see that concentric tube type of heat exchanger now, see, there is a one tube and there is a another tube which is concentric to previous one. Okay, right? Let us assume in the inner fluid hot fluid passes. So hot fluid passing through the inner fluid. This is the hot fluid. Hot fluid passing through the inner tube. Whereas cold fluid, let us assume that cold fluid passes through the cold fluid. This is the cold fluid. Cold fluid passes through the outer cylinder. Right, so see here, that cold fluid and the hot fluid are in contact at a time, but not in direct physical contact, right? Both the fluids are separated by this wall. Both the fluids are separated by this wall. See, both the fluids are separated by this tube wall. By this tube wall. Both the fluids are separated by this tube wall. Right, so that is known as the transfer type of heat exchanger or recuperator, right? Another example, the first example is a concentric tube type of heat exchanger. Another example is shell and tube type of heat exchanger, right? There is a shell, and in the shell there are number of tubes, right? In the shell there are number of tubes. So in the shell there is another fluid. In the shell there is a one fluid, and in the tube there is another fluid, right? Both the fluids are not in direct contact. Both are contact at a time, but not in direct contact. Is it fine? That is known as the transfer type of heat exchanger or recuperator. Okay, so this is the first classification. This is the first classification. Now come to the second classification. Right. The second classification is on the basis of relative direction of motion of the fluids. Right. Relative direction of motion of the fluids. So first one is a parallel flow or co-current flow heat exchanger. Second one is a counter flow heat exchanger, and third one is a cross flow heat exchanger, right? So in a parallel flow heat exchanger, if let us assume that hot fluid flowing in this direction, hot fluid is flowing in this direction, that means positive x direction. So that cold fluid is also flowing in the positive x direction. And if the hot fluid is flowing in the negative x direction, cold fluid is also flowing in the negative x direction. That means direction of both the fluids are same. That is known as the parallel flow heat exchanger or co-current. Parallel flow heat exchanger or co-current. So this is the cold fluid. This is the cold fluid. This is the cold fluid. This is the cold fluid, right? And this is the hot fluid. This is the hot fluid. right? So direction of flow of both the fluids are same, right? Now second one is a counter flow heat exchanger. Second one is a counter flow heat exchanger. So in a counter flow heat exchanger, just opposite to the parallel flow heat exchanger, right? The direction of both the fluids are opposite to each other, opposite to each other. So if cold fluid or if the hot fluid, let us assume if the hot fluid is flowing in this direction, that means positive x direction. So what is the direction of the cold fluid? What is the direction of the cold fluid? The direction of the cold fluid is opposite to the hot fluid, opposite to the hot fluid. So this is a cold fluid, and this is the hot fluid. This is the hot fluid. Fine. Now come to the next one is a cross flow heat exchanger, right? Next one is a cross flow heat exchanger. So in the cross flow heat exchanger, see, hot fluid and the cold fluid cuts orthogonally. So let us assume if this is the direction of flow, this is the direction of flow of hot fluid, direction of flow of hot fluid, right? And this is the direction of flow of cold fluid. Right, so this is a cold fluid and this is a hot fluid. So cold fluid and the hot fluid, right, meets at 90 degree, or I can say hot fluid and the cold fluids cuts. The direction of motion of the hot fluid and the cold fluid are at 90 degree or orthogonally, okay, normal to each other. Fine. So this is a cross flow heat exchanger. So this is the cross flow heat exchanger. This is the counter flow heat exchanger, and this one is a parallel flow heat exchanger. So this one is a second classification on the basis of relative direction of motion of the fluids: parallel flow, counter flow, and the cross flow. Okay, now come to the next classification. Okay, so this is the same nature of heat exchanger. This is the same. Okay, now next classification is on the basis of phase change. Next classification is on the basis of the phase change, right? So on the basis of phase change, there are two types of heat exchanger. One is the evaporative type of heat exchanger, and second one is a condenser type of heat exchanger. So in a evaporative type of heat exchanger, there is vaporization. There is a vaporization of the one fluid. Whereas in the condenser type of heat exchanger, there is a condensation of the one fluid. That means I can say in the phase change of heat exchanger, or if you classify the heat exchanger on the basis of phase change of the fluids, right? So there are evaporator type of heat exchanger and the condenser type of heat exchanger, and there is one thing is common, that is a phase change of one liquid. Right? And in the evaporator type of heat exchanger, that vaporization occurs, and in the condenser type of heat exchanger, there is a condensation of one liquid occurs, right? So if you see the evaporator type of heat exchanger, now see here, evaporator type of heat exchanger, right? Try to understand the concept of evaporator type of heat exchanger, right? See here. Evaporator type of heat exchanger. So in evaporator type of heat exchanger na, okay, there is a liquid, and that liquid is converted into vapor. There is a liquid, and that liquid is converted into vapor. So if liquid converted into vapor, so latent heat of vaporization is required na? Here the latent heat of vaporization is required. To convert the liquid into vapor, latent heat of vaporization is required now. Latent heat of vaporization is required, right? So from where this liquid is getting the latent heat of vaporization? from where the liquid is getting the latent heat of vaporization, right? Now, see here. There is a hot fluid. There is a hot fluid. Let us assume hot fluid initial temperature is Thi. There is a hot fluid. Let us assume that hot fluid initial temperature is Thi, right? And this hot fluid gets cooled down. So what is the outer temperature? This outer temperature is The, right? So hot fluid gets cooled down. This hot fluid gets cooled down. So when the hot fluid gets cooled down, so it releases some energy, na? It releases some energy, yes or no? It releases some energy, na? When the hot fluid gets cooled down, then it releases some energy, and that energy is used as a latent heat of vaporization for the phase change of liquid, right? So see here that liquid phase is there, na? Here the liquid phase is there. So I can say this is the inlet temperature of the cold fluid, right? Now see, phase change occurs, and we know that when phase change occurs, na, the temperature is constant. When phase change occurs, temperature is constant. So this is the TCE, right? See, we know that, na, ki we at the 1 atmospheric pressure, when the water is converted into steam, what is the temperature? The temperature is 100 degrees Celsius, na? And this 100 degrees Celsius is constant in the phase change, right? So here the temperature is, when phase change is there, here that liquid phase, and here vapor phase, right? So latent heat of vaporization is required. So latent heat of vaporization, from where this fluid is getting the latent heat of vaporization, see here that hot fluid gets cooled down, and this heat energy, which is obtained from the cooling of the hot fluid, that is used as a latent heat of vaporization. Is it clear? So this is the evaporator type of heat exchanger, because vaporization of the one liquid occurs here, right? And in the similarly condenser type of heat exchanger, see here, in a condenser type of heat exchanger, so this is the x is equal to 0, and this is the x is equal to L. Now see here, in the condenser type of heat exchanger, okay, so in the condenser type of heat exchanger, condensation of one fluid occurs, So when condensation occurs, so it releases the latent heat of condensation, na? When vapor converted into liquid, so it releases the latent heat of condensation. Latent heat of condensation, right? So this is the inlet temperature. So I say this is the THI, and I say this is the THE, right? And here that phase is vapor phase, and here the phase is liquid phase, right? The latent heat of condensation releases. So this latent heat of condensation, which is released here, during the phase change, this latent heat is absorbed by the cooling fluid. Right? And when the cooling fluid absorbs this latent heat, that cooling fluid is heated. So here that temperature is TCI, cold fluid inlet temperature. So cold fluid inlet temperature, that is TCI, right? That cold fluid gets the that cold fluid take the energy during take the energy, right, this energy, latent heat of condensation, right, take the energy and it is heated like this. So this is the exit temperature of the cold fluid. This is the exit temperature of the cold fluid. Is it clear? So in a condenser type of heat exchanger, that one fluid is condensed, latent heat of condensation is released, and that latent heat of condensation is absorbed by the cooling fluid. Now cooling fluid is heated. Is it clear? So this is the condenser type of heat exchanger. So this is the evaporator type of heat exchanger. This is the evaporator type heat exchanger. This is the evaporator type of heat exchanger, and this is the condenser type heat exchanger. This is the condenser type of heat exchanger. Okay, fine, right? So this is the classification of heat exchanger. This is the classification of heat exchanger, right? Now come to the next part, which is the energy balance in the heat exchanger. Come to the next part, energy balance in the heat exchanger, right? So to understand the energy balance in the heat exchanger, I am considering a concentric tube type of heat exchanger. I am considering a concentric tube type of heat exchanger. I already discussed na what is a concentric tube type of heat exchanger. So this is the one tube, and surrounding to this tube there is another tube. Concentrically there is another tube. Okay. Okay. Now see, what is the length? The length is L. This is a concentric tube type of heat exchanger. The length is L. This is the length L. Okay. Now this is inner radius. This is the inner radius, which is a R1. This is the inner radius, which is a R1. Right. And this is the, see, this is the thickness. Right, this is the R1. This is the R1, and this is the R2. This is the R2. This is the R2, right? And this is thickness of this tube. Okay, I hope you can understand this. Okay, fine. Now this radius is R1. So I am saying this radius is R1. This radius is R1 and this radius is R2. This radius is R2. Is it fine? Now let us assume that cold fluid. Let us assume that cold fluid passing through this annular space. Cold fluid passing through this annular space. So this is the inlet temperature of the cold fluid and this is the exit temperature of the cold fluid, right? So this is a cold fluid. Cold fluid. Cold fluid. Cold fluid. And the hot fluid passes through the inner tube. Right? Hot fluid is passing through this inner tube. So this is the hot fluid. Hot fluid. Is it fine? And the mass flow rate of the cold fluid is m dot C, and the specific heat at the constant pressure is CPC. Right? Whereas the cold fluid, mass flow rate of the cold fluid is m dot H and the specific heat is CPH. Specific heat is CPH. Okay, so first I take some assumptions, and what are those assumptions? That first assumption, right? That first assumption is steady state condition is maintained. That first assumption is steady state condition is maintained. This is the first assumption, right? Whatever steady state condition is maintained, that means there is no rate of change of mass, there is no rate of change of energy. Whatever the mass is entering, the same mass is leaving out, right? Whatever the mass is entering, if let us assume consider the cold fluid. So whatever the mass is entering, the same mass is leaving, right? Same thing is applicable for the hot fluid also. And this is x is equal to 0 now. This is x is equal to 0 and this is x is equal to, fine. So first assumption is steady state condition is there. Second assumption is adiabatic. Heat exchanger is adiabatic. Heat exchanger is adiabatic. What is the meaning of that? There is no heat transfer to the surrounding, right? See, this is a complete system. This heat exchanger is a complete system. This is complete system. Right? Surrounding is this side. Surrounding. Right? So there is no heat transfer or there is no heat exchange with the surrounding. See, there is a heat exchange between the hot fluid and the cold fluid because this is a part of the system only. But there is no heat transfer to the surrounding. Right? So I say that heat exchanger is adiabatic or adiabatic heat exchanger. Heat exchanger is adiabatic or adiabatic heat exchanger. Right? Now see here. If you apply the energy balance, or simply you can say that first law of thermodynamics. If you apply the energy balance or first law of thermodynamics, energy balance. First law of thermodynamics, that energy balance is nothing but the first law of thermodynamics only. First law of thermodynamics. So I can say, see, that hot fluid gets cooled down, that means its enthalpy rate decreases. Whereas the cold fluid gets heated, so its enthalpy rate increases. So simply I can say the rate of decrease of enthalpy rate of decrease of enthalpy rate of hot fluid, is equal to is equal to rate of is equal to rate of increase of rate of increase of enthalpy rate rate of increase of enthalpy rate of cold fluid of cold fluid right of cold fluid of cold fluid. So what is the rate of decrease of the enthalpy rate of the hot fluid? So this is a m dot c p of hot fluid to cp of hot fluid to Thi minus The. So this is the rate of decrease of enthalpy rate of the hot fluid. That is equal to m dot Cp of cold fluid Tc exit minus Tc inlet. So this is the rate of increase of enthalpy rate of the cold fluid. Right, so this is a simple energy balance, or you can say the heat energy lost by the hot fluid is equal to heat energy gained by the cold fluid. Simple. Is it clear? And this is equal to the actual rate of heat transfer also. No? If I ask you what is the actual rate of heat transfer, so actual rate of heat transfer either you can calculate by using this mathematical expression, or you can you are getting by using this mathematical expression, right? This also gives the actual rate of heat transfer, this also gives the actual rate of heat transfer. Is it clear? Now see here, this is the energy balance. Now use the heat transfer concept, right? Till the here we are not using the concept of the heat transfer, because this is a concept of the thermodynamics. This is the concept of the thermodynamics. You simply apply the first law of thermodynamics. Now I am using the concept of the heat transfer. So this actual rate of heat transfer, whatever the calculated from the energy balance, this is equal to that is u into a into theta. That is equal to u into a into theta. What is u? We already discussed. This u is overall heat transfer coefficient. Overall heat transfer coefficient. Overall heat transfer coefficient. Overall heat transfer coefficient. This u is the overall heat transfer coefficient. Is it clear? Now what is this is the u, this is the overall heat transfer coefficient, and next one is a. What is the a? This a is area of heat exchanger. This a is area of heat exchanger, right? And what is the theta? That theta is temperature difference. That theta is temperature difference. That theta is temperature difference, right? So here I will discuss about this temperature difference here, because this temperature difference is very, very important, right? Now see, if you see the temperature difference, which temperature difference I take? Because if you see the heat exchanger, no? if I draw the temperature variation, of hot fluid and the cold fluid, so this is the x is equal to 0, this is the x is equal to L, right? Hot fluid, this is the temperature drop of the hot fluid, right? And this is the temperature increase of this is the TCI, and this is the TCE. Is it clear? Right. That hot fluid inlet temperature, hot fluid exit temperature, cold fluid inlet temperature, cold fluid exit temperature. Is it clear? Right. So this is the temperature variation of hot fluid and the cold fluid. Now, theta, that theta is a temperature difference. So where you take that from where we take the temperature difference? Here at x is equal to 0, because let us assume at x is equal to 0, I am taking the temperature difference. This is the temperature difference now. Say this is the theta 1. At x is equal to L, the temperature difference is theta 2. The temperature difference is theta 2. So what is the theta? What is the theta? The theta is theta 1, or theta is theta 2, or theta is theta 1 plus theta 2 by 2. That means arithmetic mean. Or theta 1 is, or theta is a geometric mean of theta 1 and theta 2, or something else. Right. So this is the question. This is the question. Which theta I take? Which theta I take? Is it clear? So from the derivation, because I am not doing the derivation here, because the derivation is not important that much here, right? If you see that full course, right? If you take the full course, so in the full course, I am completely deriving it, but right now I am not deriving it, right? So directly I can write that theta, this theta is, right? When derivation is performed, then you are getting this theta as logarithmic mean sorry, logarithmic mean of theta 1 and theta 2. Logarithmic mean of theta 1 and theta 2. That means theta is equal to theta 1 minus theta 2 divided by natural log theta 1 by theta 2. Natural log theta 1 by theta 2. What is the theta? That theta is theta 1 minus theta 2 divided by natural log theta 1 by theta 2. This is the logarithmic mean of theta 1 theta 2, right? So this is known as this theta is logarithmic mean temperature difference na? Logarithmic mean temperature difference na? Logarithmic mean temperature difference na? So this is logarithmic mean temperature difference, LMTD. So in question if asked find the LMTD, so this is the LMTD. Theta 1 minus theta 2 divided by natural log theta 1 by theta 2. Is it clear? Now in this mathematical expression, theta is a temperature difference, A is the area of heat exchanger. What is the U? That U is the overall heat transfer coefficient, which already discussed. Overall heat transfer coefficient. Right? U is the overall heat transfer coefficient, which already discussed. Okay. Now see here. So this is the parallel flow heat exchanger. No? This is the parallel flow heat exchanger. If someone asks you, find out the LMTD for the parallel flow heat exchanger. If THI given, THE given, TCI given, TCE given, and if someone asks you, or in the problem it is asked that find the LMTD, then you can easily calculate the LMTD from here, right? So this is the parallel flow heat exchanger. This is the parallel flow heat exchanger. Parallel flow heat exchanger. Now come to the next, counter flow heat exchanger. Next one is counter flow heat exchanger. Counter flow heat exchanger. So in counter flow heat exchanger, so again I am considering the temperature variation. So this is x is equal to 0. This is x is equal to L. And this is the temperature of the hot fluid. This is the temperature of the this is the inlet temperature of the hot fluid. This is the exit temperature of the hot fluid. right? And this is the inlet temperature of the cold fluid, and this is the exit temperature of the cold fluid. Okay, right? So at x is equal to 0, the temperature difference is theta 1. At x is equal to 0, the temperature difference is theta 1. And at x is equal to L, the temperature difference between the hot fluid and the cold fluid, that is theta 2. Okay? So find the LMTD. Find the LMTD. So LMTD is equal to LMTD, logarithmic mean temperature difference, that is theta 1 minus theta 2 divided by natural log theta 1 by theta. Right? So important thing is there that theta 1, see, please try to understand that theta 1 is the temperature difference of the hot fluid and the cold fluid at x is equal to 0. Whereas the theta 2 is the temperature difference between the hot fluid and the cold fluid at x is equal to L. Is it fine? Okay. Now, see here. Now I am comparing the LMTD of the parallel flow heat exchanger and the counter flow heat exchanger, right? LMTD of parallel flow heat exchanger and the counter flow heat exchanger under certain constraint, right? And what are those constraints? What are those constraints? That constraint is, see here, hot fluid inlet temperature, hot fluid exit temperature, cold fluid inlet temperature, cold fluid exit temperature, right? Area of the heat exchanger, that is same in both the configuration, same, right? And I'm giving the values, numerical values. So I'm giving THI, let us assume this is 90 degrees Celsius, fine. And THE, let us assume this is the 60 degrees Celsius, this is 60 degrees Celsius. And the cold fluid inlet temperature I am taking as 30 degrees Celsius. And cold fluid exit temperature, let us assume this is 40 degrees Celsius. 40 degrees Celsius. Now calculate the LMTD. If configuration is parallel flow, then find out the LMTD. LMTD in case of the parallel flow. So what is the theta 1 in case of the parallel flow? In case of the parallel flow, THI minus TCI, na? THI minus TCI. THI minus TCI. So 90 minus 30. 90 minus 30, that is 60. Right, theta 1. And what is the theta 2? That is a THE minus TCE. So that is 20. So that is 60 minus 20, natural log 60 by 20. So from here you can calculate the LMTD, na? LMTD you can calculate. So what is the LMTD you are getting? That is 60 minus 20 ln 60 by 20. So this is 36.41. 36.41 degrees Celsius or Kelvin. So same, na? Because that is a temperature difference. So temperature difference either is in Kelvin or degrees Celsius. Meaning is same because this is a temperature difference, logarithmic mean temperature difference. Right? So either you can say 36.41 degrees Celsius or you can say 36.41 Kelvin. Now come to the LMTD. LMTD in case of counter flow heat exchanger. Counter flow heat exchanger, that is equal to. So in counter flow heat exchanger, that is, what is theta 1? That theta 1 is THI minus TCE. THI minus TCE. So that is 90 minus 40, and 90 minus 40, that is 50. Minus THE minus TCI, that is 60 minus 30, and 60 minus 30 is 30. Divided by natural log 50 by 30, and that is equal to, see here, this is 50 minus 30 natural log 50 by 30, and this comes 39.15 degrees Celsius or Kelvin. Right. So what you are conclude from here? What you can conclude from here? That conclusion is, if this condition is exist, if this condition is exist, right, then I can say LMTD of counter flow is greater than the LMTD of parallel flow. Is it clear? And if you consider the cross flow, how you find the LMTD of the cross flow? So LMTD of cross flow is equal to F multiplied by LMTD of counter flow. And what is F? This F is known as correction factor. And this F value is less than 1. This F value is less than 1. Right. So if the problem is based on the cross flow heat exchanger, then definitely the correction factor value is given. Right. So LMTD for the cross flow is F multiplied by LMTD of the counter flow. Is it clear? So if you consider the cross flow heat exchanger also, so what is the relation? This relation is there. LMTD of counter flow, then LMTD of cross flow, then LMTD of cross flow, then LMTD of parallel flow. Right? This relation is applicable. Is it clear? Right? And if I'm assuming that, next slide, let U, which is the overall heat transfer coefficient, this is also constant. This U is also constant. The overall heat transfer that overall heat transfer coefficient is also same, also constant in both the case. Then what is the relation between the heat transfer? Right. So area is same. See here, Q dot is equal to, that is U into A into LMTD na. That Q dot is equal to U into A into LMTD na. So U is same, A is same. Right. So Q dot is dependent on LMTD, and LMTD for the case LMTD is more, the rate of heat transfer will be more, right? So I can say that Q dot, which is the rate of heat transfer in counter flow, is greater than the rate of heat transfer cross flow, and the list you are getting in parallel flow. Under the conditions. What are the conditions? Area same. Overall heat transfer coefficient is same. Right. Hot fluid inlet exit temperature, cold fluid inlet exit temperature is same. Under these conditions. Is it fine? Okay. Now see. So this is the important part. Now come to the very, very important part, which is a special case of counter flow heat exchanger. special case of counter flow heat exchanger. Special case of counter flow heat exchanger. And what is that special case? That special case is both the fluid, if both the fluids, if both the fluids having same if both the fluids having same heat capacity rate, heat capacity rate, if both the fluid having same heat capacity rate, or you can say equal heat capacity rate. Okay, fine, same or equal heat capacity rate. So what is the heat capacity rate? C is the specific heat, na? This C is the specific heat, na? C is a specific heat. C is a specific heat. And what is the M into C? This is the heat capacity. This is the heat capacity. And what is the M dot C? What is the M dot C? This is the heat capacity rate. What is the M dot C? That is the heat capacity rate. So if both the fluid having same heat capacity rate, that means mass flow rate into C, product of M dot C for the hot fluid, this is the heat capacity rate of the hot fluid, is equal to heat capacity rate of the cold fluid, Cp, cold fluid. If heat capacity rate are equal, then, so if you see the energy balance, no? If you see the energy balance, so I directly write here energy balance, no? Directly I write the energy balance. So that is M dot C of hot fluid inlet temperature, hot fluid exit temperature is equal to, this is the M dot C cold fluid exit temperature, cold fluid inlet temperature. Is it clear? You can write C also, na? Because see that Cp concept come in case of the compressible substance. If there is a incompressible substance, if there is a water or oil, there is only specific heat, right? But if there is a compressible substance, if there is some gases or some air is there, right, then the Cp come into picture, because incompressible substance there is a concept of Cp and Cv. But in case of the incompressible substance, there is only concept of the specific heat, right? So I write here C only, but if compressible substance is there, then simply you can write the Cp. Simple, right? Now see, MC of the hot, आपके पास heat capacity rate of the hot fluid is equal to heat capacity rate of the cold fluid, right? So ultimately you are getting this. See, Thi minus The is equal to Tce minus Tci. Now see here, Thi minus, simply arrange this mathematical expression. So Thi minus Tce, and this is The minus Tci. And in case of the counter flow heat exchanger, see this term. In case of the counter flow heat exchanger, see this term, Thi minus Tce. This is equal to theta 1. This is equal to theta 1. And this term is equal to theta 2. This term is equal to theta 2. That means, if you see the counter flow heat exchanger, with equal heat capacity rate, then there is a equation, theta 1 is equal to theta 2. This is very, very important, that theta 1 is equal to theta 2. This equation you are not getting in the parallel flow heat exchanger. Parallel flow heat exchanger with equal heat capacity rate, you are not getting this, right? There is possibility of the parallel flow with equal heat capacity rate also, but in a parallel flow equal heat capacity rate there is no problem, you are not getting theta 1 is equal to theta 2, but in counter flow with equal heat capacity rate you are getting theta 1 is equal to theta 2. And if you are going to calculate, the LMTD, if you are going to calculate the LMTD, so LMTD is theta 1 minus theta 2, natural log theta 1 by theta 2. Is it clear? Is it clear? Right. So what is the you are getting 0 by 0 form now, because theta 1 is equal to theta 2. Theta 1 is equal to theta 2. So if theta 1 is equal to theta 2, then you are getting the 0 by 0 form. If 0 by 0 form is there, that is the indeterminate form. And in the indeterminate form, right, to find out the LMTD, if indeterminate form came, right, and you want to find out the LMTD, then go for the limit concept. In mathematics there is a concept of limit, na? Right? So by using the limit concept we can find out the LMTD, because directly I am not able to find out the LMTD here, because that is a 0 by 0 form. Fine. Now see the LMTD. So to find out the LMTD in this case, use the limit concept. Use the limit concept, right? And I'm not saying theta 1 is equal to theta 2. I'm saying theta 1 approaches to theta 2, or theta 2 approaches to theta 1, right? I'm saying that theta 1 is not equal to theta 2. Theta 1 approaches to theta 2. Theta 1 approaches to theta 2, right? Theta 1 approaches to theta 2. Now see, 0 by 0 form is there, na? 0 by 0 form is there. So if 0 by 0 form is there, then we are using the L'Hospital rule in mathematics, na? L'Hospital rule, right? And in the L'Hospital rule, differentiate the numerator with respect to variable and differentiate the denominator with respect to variable, right? And what is the variable here? The theta 1. Theta 1 is a variable because theta 1 approaches to theta 2. The value of theta 1 will change, right? So if you are differentiating here, limit theta 1 approaches to theta 2, so theta 1 minus theta 2, so this is 1 divided by, right, this is 1 upon theta 1 by theta 2 into 1 upon theta 2. So 1 by theta 2 cancel out. So ultimately what you are getting this theta 1. This is theta 1. So in this case, what is the LMTD? That LMTD is theta 1. And similarly, if you are assuming that theta 2 approaches to theta 1, and similarly, if you are assuming that theta 2 approaches to theta 1, in this case, you are getting LMTD as theta 2. So ultimately, I can say that LMTD is equal to theta 1 is equal to theta 2. LMTD is equal to theta 1 is equal to theta 2. So this is a special case. Counter flow with equal heat capacity rate, right? And such type of heat exchanger is known as the balanced. Such type of heat exchanger is known as the balanced type of heat exchanger. So whenever in question it is mentioned that balanced type of heat exchanger, right? Balanced type of heat exchanger, that means it is counter flow with equal heat capacity rate. Counter flow with equal heat capacity rate. Is it clear? Is it clear to everyone? Okay, now see so this is the balanced type of heat exchanger. And in a balanced type of heat exchanger, if you want to see the temperature variation of the hot fluid and the cold fluid, temperature variation of the hot fluid and the cold fluid, temperature variation of the hot fluid and the cold fluid, right? So theta 1 is equal to theta 2. How the temperature varies? How the temperature varies with respect to x? So see here, this is x is equal to 0 now. This is x is equal to L. This is x is equal to L, right? So let us assume randomly, I am assuming that, see here, this temperature is Thi na, and this temperature is The, right? So let us assume that temperature varies like this. Temperature varies like this. And this is the inlet temperature of the cold fluid na, and this is the exit temperature of the cold fluid. Okay, fine. Okay. Right. So this is the temperature variation of the hot fluid, and this is the temperature variation of the cold fluid. I am assuming. Let us assume. Okay. Now see here. Now see here. I am considering a small element. I am considering a small element at a distance x. At a distance x, I am considering a small element. A small element. And this thickness is dx. I am assuming this thickness as dx. Okay. And the temperature difference for the hot fluid, temperature difference for the hot fluid is dTh, and temperature difference for the cold fluid, that is dTc. That is dTc, right? So if you apply the energy balance for this portion, so we can say na, that energy balance for this portion, right, that dq dot is equal to, this is the m dot c of hot fluid, right, m dot c of hot fluid, and dTh is equal to m dot c of cold fluid, dTc is equal to, that is u into dA into, right, and that is Th minus Tc. Th minus Tc. What is the temperature difference? What is the temperature difference between the hot fluid and the cold fluid for this small element? See, hot fluid temperature difference is dTh. Cold fluid temperature difference is dTc. But what is the difference between the hot fluid and the cold fluid at a x distance? So I say hot fluid temperature for this small element, dx is very, very small element na. So for this small element, hot fluid temperature is Th, hot fluid temperature is Th, and the cold fluid temperature is Tc. Is it fine? And what is the dA? The dA, that is the small elemental area. So that small elemental area, let us assume perpendicular to the monitor, there is a width, and that width is b. That width is b, so that is b into dx. B into dx. Is it fine? Now, see this two term, right? So from here you can say, see here, m dot c of hot fluid, dTh is equal to m dot c dTc, right? Because equal heat capacity rate is there na? So these two terms are cancelled out. So ultimately you are getting this dTh minus dTc is equal to 0, and if you are integrating this, you are getting Th minus Tc is equal to constant. Th minus Tc is equal to constant. And what is the meaning of that? The meaning is that at any distance x, the temperature difference between the hot fluid and the cold fluid is constant. It is not changing with respect to x, right? And what is the meaning of that? That meaning is that, right, that hot fluid temperature profile and the cold fluid temperature profile, is parallel to each other. How you are getting the Th minus Tc is equal to constant? How you are getting at every x Th minus Tc is equal to constant? When the temperature profile is parallel. When the temperature profile is parallel, then you are getting Th minus Tc is equal to constant. That means I can say now that Th minus Tc is not function of x. Not function of x. So this is the first thing. So from here, from this exercise, it is clear that hot fluid temperature profile and the cold fluid temperature profile is parallel to each other. Parallel to each other. But there are number of possibilities, no? Okay. There are number of possibilities to draw a parallel lines. There are number of possibilities. Right. Now see, next. Lines are parallel, it is clear, but actually lines are parallel, right? But parallel lines are possible like this also, no? These are also parallel lines, these are also parallel. So which type of parallel? Which type of parallel? Now see here, now see, now take these two, m dot c h dth is equal to u into, and u is not a function of x, na? I am assuming this u is constant, u is not a function of x. The overall heat transfer coefficient is not a function of x, that is constant. I am assuming that u is not function of x, u is constant, right? Now see here, u into, that is b into dx, and that is Th minus Tc, right? Now see here, dTh by dx is equal to, this is u into b into Th minus Tc divided by this is m dot c of hot fluid, right? Now see here, this term is constant, this is not a function of x. This term is constant, not a function of x. This term is also constant, not a function of x, right? This term is also constant, not a function of x. That means I can say na, dth by dx is not a function of x, that is constant. What is the meaning of that? That means temperature, that means slope of temperature profile of the hot fluid. What is this? What is the dTh by dx? This is the slope of temperature profile of the hot fluid, na? This is a hot fluid temperature profile slope, na, dTh by dx. So this dTh by dx is constant. That means, what is the meaning of that? That slope is constant. That means it is a straight line. Slope is constant, that means it is a straight line. And similarly I can say this dTc by dx is equal to constant, right? So from here I can say the slope of temperature profile of the cold fluid is straight line, because slope is constant, right? That means that temperature profile is parallel to each other. That means temperature profile is parallel to each other and straight line, right? For the balanced type of heat exchanger, so temperature profile, this is the correct temperature profile. This is the correct temperature profile. This is x is equal to 0, x is equal to L. Now this THI, right? And this is THE. Fine. Okay. Parallel to each other and straight line. So this is TCI and this is TC, right? This is TCI and this is TCE. So these two lines are parallel to each other and the straight line. So this is the temperature profile for the balanced type of heat exchanger. Balanced type of heat exchanger. So balanced type of heat exchanger is counter flow heat exchanger with equal heat capacity rate. Right? Okay. Now come to the next evaporator type of heat exchanger and the condenser type of heat exchanger. Next type of heat exchanger is evaporator type heat exchanger, evaporator type heat exchanger or condenser type of heat exchanger, evaporator type of heat exchanger and condenser type of heat exchanger, condenser type of heat exchanger, condenser type of heat exchanger. Right? Now see here, if there is a heat exchanger in which one liquid phase change occurs, if there is a heat exchanger in which one liquid phase change occurs, then it is immaterial, the flow is parallel flow or counter flow. Right? Because if flow is parallel, then you are getting the LMTD that is same as if you are assuming the flow is counter and you are getting the LMTD. Right? So I can say in evaporator type of heat exchanger and the condenser type of heat exchanger, if you are calculating the LMTD, LMTD. So if your flow is parallel, that is same as counter. Right? If there is a evaporator type of heat exchanger or condenser type of heat exchanger, right, that LMTD does not depend on the type of the flow. That means type of the flow means parallel flow or counter flow. The heat exchanger is a parallel flow heat exchanger or counter flow heat exchanger. If it is a evaporator or condenser type of heat exchanger, then LMTD will be same in both the heat exchanger, parallel flow as well as counter flow. Is it clear? And that is the reason if the question is asked the evaporator type of heat exchanger or condenser type of heat exchanger, if in question it is mentioned that this is a condenser type of heat exchanger or this is a evaporator type of heat exchanger, in question it is never told about the which type of flow is there. It is a parallel flow or counter flow. Never. It is never mentioned in the problem. It is clear, right? Now see from one example. Let's discuss with one example. I am considering an example. Right? So let us assume I am considering a counter flow, let us assume I am considering a condenser type of heat exchanger. Condenser type of heat exchanger, see. Condenser type of heat exchanger. Right? And that hot fluid is condensed. So here the temperature is 100 degrees Celsius. Here also temperature is 100 degrees Celsius, na? Because when the phase change is there, temperature is constant. Right? And it releases the latent heat of condensation. And that latent heat of condensation is utilized by the cold fluid. So cold fluid inlet temperature is 30 degrees Celsius and cold fluid exit temperature is 60 degrees Celsius. Right? Which type of flow it is? It is parallel flow heat exchanger. It is parallel flow. So if you are calculating the LMTD, here, LMTD parallel, that is equal to, now what is the LMTD? This is x is equal to 0 now. This is x is equal to 0. This is x is equal to L. Right? And this is the theta 1 now. This is the theta 1. This is the theta 2. Right? So this is 100 minus 30. LMTD parallel. 100 minus 30. 100 minus 30, that means it is 70. It is 70. It is 70 minus, sorry. It is 70. 100 minus 30, 70 minus 100 minus 60, 40 divided by natural log 70 by 40. And if you are calculating the LMTD, then it is 70 minus 40 ln 70 by 40. Then it is 53.61. It is 53.61 degrees Celsius or Kelvin. Right? This is the LMTD when you are assuming flow is parallel. Now, if you are assuming flow is counter, condenser type of heat exchanger and counter flow heat exchanger. So this is the hot fluid inlet temperature, again 100 degrees Celsius, hot fluid exit temperature, that is hot fluid exit temperature 100 degrees Celsius. Right, and this is the cold fluid inlet temperature, and this is the cold fluid exit temperature. What is the cold fluid inlet temperature? This is cold fluid inlet temperature. That cold fluid inlet temperature is 30. This is 30 degrees Celsius. And cold fluid exit temperature, that is 60 degrees Celsius. 60 degrees Celsius. This is x is equal to 0. X is equal to 0, and this is x is equal to L. Right? Counter flow. Okay, now find out the theta 1. LMTD. In this case, LMTD. Counter flow, na? Counter flow. Then find out the LMTD. So theta 1 again 100 minus 60, that is 40. Right, what is theta 2? 100 minus 30, 70. Natural log 40 by 70. Natural log 40 by 70. Or simply you can say na 70 minus 40 natural log 70 by 40. You are getting the same, which is equal to 53.61 degrees Celsius or Kelvin. 53.61 degrees Celsius or Kelvin. Is it clear? Is it clear? So in a phase change heat exchanger, right, if phase change of one fluid occurs, then it is immaterial. In that heat exchanger, is flow is parallel flow or counter flow. It is immaterial because you are getting the same LMTD. Fine. Now come to the next concept, that is the concept of effectiveness. Come to the next concept, and that concept is effectiveness concept. Effectiveness concept. Effectiveness of the heat exchanger. That effectiveness of the heat exchanger. Effectiveness of the heat exchanger. So what is the effectiveness? What is the effectiveness? So this effectiveness is, this is the actual rate of heat transfer. This is the actual rate of heat transfer from the heat exchanger to maximum rate of heat transfer. To maximum rate of heat transfer. To maximum rate of heat transfer. This ratio is known as the effectiveness of the heat exchanger. The actual rate of heat transfer from the heat exchanger to maximum rate of heat transfer to the heat exchanger. So what is the actual rate of heat transfer? How you calculated this? How you calculate this actual rate of heat transfer? So this is equal to hot fluid inlet temperature, hot fluid exit temperature. This is the actual rate of heat transfer, and this is also equal to m dot c and cold fluid exit temperature minus cold fluid inlet temperature. And also remember that very beautiful concept, na? That concept is, see, that m dot c into this is the delta T. This is constant. This is constant. See here. This is the m dot c, this is the m dot c, this is the temperature difference, right? So the product of heat capacity rate, the product of heat capacity rate and the delta T is constant now, because this multiplied by, see, if I write here x1 y1 is equal to x2 y2 is equal to x3 y3, what is the meaning of that? X into y is equal to constant na yaar. X into y is equal to constant na. And similarly, if I write here m dot c, heat capacity rate multiplied by, right, this is the temperature difference of the hot fluid is equal to heat capacity rate of the cold fluid multiplied by temperature difference of the cold fluid. That means the product of heat capacity rate and the delta T is constant. So if delta T is more, if delta T is more, then heat capacity rate will be less, or I can say if heat capacity rate will be more, if heat capacity rate will be more, the delta T will be less, right? Or if heat capacity rate is less, the delta T will be more, right? So this concept is used here. So remember this concept. The product of heat capacity rate and the temperature difference is constant, right? So remember this concept, no? This concept is used here. Okay. Now see. This is the actual rate of heat transfer. Now come to the maximum rate of heat transfer. What is the maximum rate of heat transfer? That maximum rate of heat transfer is, see, the maximum temperature difference in the heat exchanger. What is the maximum temperature difference in the heat exchanger? That is hot fluid inlet temperature minus cold fluid inlet temperature. This is the maximum temperature difference, right? In a particular heat exchanger, this is the maximum temperature difference, THI minus TCI, right? So to get the maximum rate of heat transfer, to get the maximum rate of heat transfer through the heat exchanger, I'm saying that, right, I'm taking the maximum temperature difference first, THI minus TCI into m dot c, into m dot c, and this m dot c is minimum. Why it is minimum? Why it is minimum? Because see, the heat capacity rate shows the energy storing capacity or heat energy storing capacity. If heat capacity rate is more energy is stored, less energy is transferred, right? If heat capacity rate is more, then more energy is stored, less amount of heat energy is transferred. And here I want a maximum rate of heat transfer. That means I want very less amount of heat energy should be stored. The maximum amount of heat energy should be transferred. So for that I want a minimum heat capacity rate. Right. So if the minimum heat capacity rate is there, if the minimum heat capacity rate is there, then if minimum heat capacity rate is there, then, right, heat energy transferred is more and the heat stored is less. That's why I'm taking a minimum heat capacity rate, right? So this is the maximum rate of heat transfer and this is the actual rate of heat transfer, and the ratio of these two gives the effectiveness, right? Ratio of these two gives the effectiveness. So I can say that effectiveness is equal to, right? Effectiveness is equal to m dot c, hot fluid inlet minus hot fluid exit, m dot c, cold fluid exit minus cold fluid inlet, to m dot c minimum heat capacity rate, hot fluid inlet minus cold fluid inlet, hot fluid inlet minus cold fluid inlet. Is it clear? So this is the effectiveness. Now I want to write the effectiveness mathematical expression in terms of temperature, directly in terms of the temperature, because sometime in question it is given like that, right? In question it is given hot fluid inlet temperature 90 degrees Celsius. See here, hot fluid inlet temperature 90, cold fluid inlet temperature, that is let us assume this is 30, hot fluid exit temperature, let us assume this is 60, and cold fluid exit temperature, let us assume this is 40. Now in question it is asked find the effectiveness. Mass flow rate is not mentioned, specific heat is not mentioned, heat capacity rate not mentioned, that only temperature is mentioned, hot fluid inlet, hot fluid exit, hot fluid inlet, hot fluid exit, hot fluid exit. No? This is the hot fluid exit, sorry. This is hot fluid exit. Hot fluid inlet, hot fluid exit, cold fluid inlet, cold fluid exit. Right? This much information is given in the problem. Now in question, ask that find the effectiveness. Find the effectiveness. Find the effectiveness. Find the effectiveness. Right? Now see here. I already told you there is one concept. That concept I discussed here, and that concept is used. Right? Now see here. M dot C minimum and maximum temperature difference. And what is the maximum temperature difference? What is the maximum temperature difference? THI minus TCI. So that is 90 minus 30. 90 minus 30. Now see here, find out the delta TH. Find out the delta TH. The temperature difference for the hot fluid. So what is the temperature difference for the hot fluid? 90 minus 60. 90 minus 60. And this is 30. Now find out the temperature difference for the cold fluid. Temperature difference for the cold fluid. Temperature difference for the cold fluid. This is 40 minus 30. 40 minus 30. That means it is 10. Is it clear? Now see here. I already told you, see here. M dot C into delta T. This product is constant. This product is constant. So if I take delta T more, so M dot C is minimum. If delta T is maximum, then M dot C is minimum. Right? Now see here. In these two, for these two, hot and cold fluid, for hot and cold fluid, right? The temperature difference is maximum for the hot fluid. Na? See here, the temperature difference is maximum is hot fluid. Na? So I'm writing here delta T for hot fluid, and automatically, if delta TH is more, then heat capacity rate for the hot fluid is less. Hot fluid, heat capacity rate for the hot fluid is minimum, M dot C of the hot fluid. And this M dot C of the hot fluid, this is equal to M dot C, minimum heat capacity rate. This is the minimum heat capacity rate. This is the minimum heat capacity rate. So you can cancel heat capacity rate from the numerator and the denominator, right? So ultimately what you are getting this delta TH, that is 30, divided by 90 minus 30, that is 60. So this is 1 by 2. So effectiveness is 0.5. Effectiveness is 0.5. Effectiveness is 0.5. So I hope you can understand this logic, right? If temperature is given, heat capacity rates are not given, then how you find the effectiveness? How you find the effectiveness? So by using this logic, you can find out the effectiveness. Okay, I hope it is clear. I hope it is clear. Okay, now come to the, so this is a concept of effectiveness. This is a concept of effectiveness. Now see here, next method is effectiveness NTU method. Next method is the effectiveness NTU method. But before that, try to understand why there is need of another method. Though we have the LMTD method. We have the LMTD method. By using the LMTD method, we can find out the area of the heat exchanger, right? By using the LMTD method, we find the area of heat exchanger. Then why there is need of another method, right? So see, LMTD method is useful. See here, Q dot is equal to U into A into LMTD. Q dot is equal to U into A into LMTD. So generally in problem U is given, right? And you are calculating the LMTD. So for calculate the LMTD, at least one fluid exit temperature should be known. At least one fluid exit temperature should be known, right? So let us assume if TCI, TCE, THI, THE, see, this is given, this is given, this is given, right? TCE, matlab cold fluid exit temperature is not given. You can find out the cold fluid exit temperature na, by using the energy balance. Okay, heat capacity rate are given. Heat capacity rate are given. You can find out the exit temperature of the cold fluid na, by using the energy balance. Yes, we can find out, sir. And if you are able to find out the temperature of temperature of inlet and the exit of hot fluid and the cold fluid, you can easily find out the LMTD. There is no problem with that, right? And once you know the LMTD, you already you know that is given in the question. That is given in the question, right? So if you know the LMTD, then you can easily calculate the area of heat exchanger. You can easily calculate the area of heat exchanger. Is it clear? Is it clear? You can easily calculate the area of heat exchanger. But if exit temperature of any fluid is not given, then if exit temperature of any fluid is not given, then if let us assume this TCE, this THE is not given, this TC is not given, only this is given, hot fluid inlet, hot fluid exit, then it is easy to calculate the exit temperature, because without exit temperature you are not able to find out the LMTD. Without exit temperature it is not possible to find out the LMTD. So if exit temperature is not given, then how you find the exit temperature, right? So for this you are using the heat and trial. So this is the one way, use the heat and trial. And there is another way, use the effectiveness NTU method. That's why that effectiveness NTU method come into picture. That's why that effectiveness NTU method is come into picture. So please try to understand, when this effectiveness NTU method is used, that effectiveness NTU method is used when that exit temperature of any fluid is not mentioned, or exit temperature of any fluid is not given, then we are using the effectiveness NTU method. So already we studied about the effectiveness, right? Now let's start our discussion on the effectiveness NTU method. Effectiveness NTU method. Effectiveness NTU method. Effectiveness NTU method. Right. Effectiveness NTU method. Effectiveness NTU method. Effectiveness NTU method. Right. So in effectiveness NTU method, that effectiveness, this effectiveness is function of two parameters. One is the NTU, number of transfer units. What is the NTU? What is the full form of the NTU? That NTU is number of transfer units. What is the NTU? That NTU is number of transfer units, right? So that effectiveness is function of NTU and the CR, right? What is the CR? What is the NTU? Right? Let's start our discussion. So first, NTU. This NTU is a ratio of UA to minimum heat capacity rate. UA to minimum heat capacity rate. This NTU is ratio of UA to minimum heat capacity rate. What is the U? That U is the overall heat transfer coefficient. What is U? U is the overall heat transfer coefficient. What is the A? Area of the heat exchanger. What is the M dot C? That is the minimum heat capacity rate. M dot C is the minimum heat capacity rate. Okay. Now see, next is CR. What is this CR? This CR is capacity ratio. This CR is capacity ratio. This CR is capacity ratio. And what is this CR? This CR is equal to minimum heat capacity rate to maximum heat capacity rate. This CR is minimum heat capacity rate to maximum heat capacity rate, right? Minimum heat capacity rate to maximum heat capacity rate, that is the CR. This is the capacity ratio. Okay. Now next is effectiveness formula, because I already told you that effectiveness is a function of NTU and the CR in the effectiveness NTU method, right? So if I'm talking about the parallel flow heat exchanger, if I'm talking about the parallel flow heat exchanger, if I'm talking about the parallel flow heat exchanger, so for parallel flow heat exchanger, for the parallel flow heat exchanger, for the parallel flow heat exchanger, for the parallel flow heat exchanger, that effectiveness mathematical expression for parallel flow heat exchanger, this is 1 minus exponential minus NTU 1 plus CR upon 1 plus CR. 1 plus CR. Right, this is the effectiveness for the parallel flow heat exchanger. This is the effectiveness for the parallel flow heat exchanger. Right, 1 minus exponential minus NTU 1 plus CR upon 1 plus CR. Right, and what is the effectiveness mathematical expression for the counter flow heat exchanger? For the counter flow heat exchanger, for the counter flow heat exchanger, for the counter flow heat exchanger, that effectiveness for the counter flow heat exchanger, that is 1 minus exponential minus NTU 1 minus CR upon 1 minus CR exponential minus NTU 1 minus CR. So this is the effectiveness, of the counter flow heat exchanger. This is the effectiveness of the counter flow heat exchanger. Right, so one is a parallel flow heat exchanger and another one is a counter flow heat exchanger. Right, now come to the special cases. Let's discuss about the special cases. Special cases. What are the special cases? What are the special cases? So special case number 1. Special case number 1. Right, when phase change is there, right, that means I'm talking about the evaporator type of heat exchanger, evaporator type heat exchanger and counter flow heat exchanger. Counter flow heat exchanger. I'm talking about the evaporator flow heat exchanger and the counter flow heat exchanger. Right. So if evaporator type of heat exchanger is there or counter flow heat exchanger is there, then we know that if phase change is there, na, if phase change is there, either it is a liquid to vapor or vapor to liquid, liquid to vapor, let us assume. Phase change is there. So during the phase change, the temperature is constant. We know that. That is known as the saturation temperature. During the phase change, the temperature is constant and we know that that temperature is known as the saturation temperature. Is it fine? So temperature is constant. So if the temperature is constant, then what is the specific heat? 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 What is the formula for, what is the unit of the specific heat? That is joule per kg Kelvin. That is joule per kg Kelvin. And what it shows? What is the specific heat? What is the definition of the specific heat? So that is that amount of heat energy. Specific heat is amount of heat energy which is required to change the temperature. 1 Kelvin or 1 degree Celsius, right, for 1 kg of substance. Or I can say amount of heat energy which is required for 1 kg of substance to change the temperature 1 degree Celsius or 1 Kelvin, right? And in this case the temperature is constant. When the phase change is there, the temperature is constant. That means there is no temperature change. If you want to change the temperature by 1 Kelvin or 1 degree Celsius, then hypothetically I can say that infinite amount of heat energy is required. Infinite amount of heat energy is required. In this case, what is the specific heat? That is specific heat is infinite. Right? In this case, what is the specific heat? The specific heat is infinite. If specific heat is infinite, that means heat capacity rate is infinite. Heat capacity rate is infinite. So there is 2 heat capacity rate, na? One for the hot fluid, another one is for the cold fluid. है ना? One for the hot fluid, another one is for the cold fluid. So what is the maximum heat capacity rate? The maximum heat capacity rate for that fluid for which that phase change is there. Right? If condensation is there, So hot fluid phase change is there, na? Condensation is there. If evaporator type of heat exchanger is there, so cold fluid phase change is there. So cold fluid having the maximum heat capacity rate in the case of the evaporator type of heat exchanger. So ultimately I can say the maximum heat capacity rate is infinite, whereas the minimum heat capacity rate is finite, where the minimum heat capacity rate is finite, some finite value. So what is the capacity ratio? The capacity ratio is minimum heat capacity rate to maximum heat capacity rate, and maximum heat capacity rate is infinite, so it is finite by infinite. It is finite by infinite. So finite by infinite, that is 0. Right? Finite by infinite, that is 0. So what is the CR? That CR is 0. What is the CR? That CR is 0. That CR is 0. So in case of evaporator type of heat exchanger, or in case of the evaporator type of heat exchanger or counterflow type of heat exchanger, the capacity ratio is 0. Capacity ratio is 0. Is it clear? So capacity ratio is 0, then if capacity ratio is 0, then what is the effectiveness of the parallel flow heat exchanger? What is the effectiveness, right? Parallel flow and counter flow, you are getting the same result. See here, 1 minus exponential minus NTU, right? You are getting this mathematical expression because CR is 0. If counter flow, so again this is 1 minus exponential minus NTU, because CR is 0, right? So you are getting the same effectiveness mathematical expression if evaporator type of heat exchanger or condenser type of heat exchanger is there, right? You are getting the same mathematical expression of the effectiveness, either it is a parallel or it is a counter. Is it clear? So this is the one case. This is the one case, first special case. This is the first special case. Now come to the second special case. Second special case. And in the second special case, if heat capacity rate are equal, so if the heat capacity rate are equal, that means minimum heat capacity rate is equal to maximum heat capacity rate. If both the fluids having the equal heat capacity rate, then minimum maximum same, na? Right? So what is the value of CR? That value of CR is equal to 1. If CR is 1, right? Now, if heat exchanger is a parallel flow heat exchanger, So parallel flow heat exchanger, effectiveness for parallel flow, so this is 1 minus exponential minus NTU 1 plus CR. CR value is 1, so this is minus 2 NTU upon 1 plus CR, so it is 2. Right? So this is the effectiveness formula for the parallel flow heat exchanger. Right? And for the counter flow heat exchanger, counter flow heat exchanger. So for the counter flow heat exchanger, that is equal to, see, 1 minus exponential minus NTU 1 minus CR. The CR value is 0. CR value is 1. So that comes 1 minus e to the power 0. 1 minus e to the power 0. Right? And in the denominator, 1 minus CR. CR value is 1. So 1 minus exponential, again it is 1 minus e to the power 0. So 1 minus 1 upon 1 minus 1, so it is 0 by 0 form. It is 0 by 0 form. If it is 0 by 0 form, then again it is an indeterminate form. It is 0 by 0 form, so again it is indeterminate form. So if it is indeterminate form, then see, indeterminate form, then how you are getting the effectiveness? By using the again limit concept. So effectiveness limit, so CR is not equal to 1 where CR approaches to 1. So 1 minus exponential minus NTU 1 minus CR upon 1 minus CR exponential minus NTU 1 minus CR, right? So ultimately what you are getting, that effectiveness, right? When you are solving this by using the L-Hospital rule, by using the L-Hospital rule, if you are solving this, what you are getting this NTU upon 1 plus NTU, NTU upon 1 plus NTU, NTU upon 1 plus NTU, right? So this is the mathematical expression for the effectiveness. This is the mathematical expression for the effectiveness. Is it clear? So this is the effectiveness NTU method, right? So in the effectiveness NTU method, right, there are a number of mathematical formulas, right? You should remember these mathematical formulas, then you are able to solve the problem. Is it clear? Is it clear? So I hope you can understand. I hope you can understand each and every topic of the heat exchanger. So this is all about the heat exchanger, right? So in heat exchanger, that is very, very important topic. That heat exchanger is very, very important topic. Almost every year you are getting the question from the heat exchanger, right? So in heat exchanger, there is a energy balance, right? LMTD method and the effectiveness NTU method, right? So this is easy part of the heat exchanger. You can score full marks from this topic. Okay, so thank you so much for today's session, this session. Okay, so we will discuss a new topic in the next session. So thank you so much, guys. Thank you.